Cool, yeah. So we're going to talk about formal verification. The main premise, well, first of all, I should say, Bob and Wen, please forgive me if I say something too egregious that you can't possibly stomach. Please do interrupt and correct me. The premise of formal verification is that both software and mathematical proofs are written by humans, and humans make an awful lot of mistakes. And the idea is that can we get computers to check our software and proofs and therefore guarantee that certain types of mistakes do not occur, and with a mathematical guarantee rather than just testing and saying, well, okay, we've tested these 10 cases and therefore we assume that they don't occur in the other infinite number of cases that are not tested.
So it assumes you've got a finite list of states you can test, right?
Yes. Well, testing. If you only have a finite list of states, then you can get through it by testing, in theory. If it's very long, then it's going to take forever for all practical purposes. But the idea of formal verification is that you shouldn't have to. It works for infinite sets of states as well.
Okay.
That you can. It should mathematically check. Its algorithm should guarantee you that there are no mistakes even in an infinite domain.
Okay. Good.
So it's a step up from testing. I'm sure there's lots of mathematical proofs that are fairly easy to visualize what you might want to check. Software maybe is slightly less clear. So properties of programs that we might want to verify is not saying that these are always possible to verify, but you might want to verify. You might want to verify that your program doesn't loop forever, so it eventually terminates, or you might want to prove that it doesn't crash, or that more abstractly it gives the right answer. The approach is to you basically reduce software down to mathematics. So you build a mathematical model of what your program does, and then you prove properties about that model.
Can I just ask a very stupid question? So,
no.
So I know things like JUnit tests, right? So that's So that's what you think, so that's what you would refer to as testing, for example?
Yeah.
Yeah, okay.
Yeah, unit tests are testing, yeah.
Okay, and then the mathematical proof is giving you a guarantee for a very large number of possible states, which you can't possibly all write unit tests for.
Yes, yeah.
Okay, good, got it.
So it works, if you have an input output, it works for all input. You prove for all inputs, not just the inputs that you test. So you compile down well, you take your program and you take your property that you want and you generate a mathematical model for it. And the resulting mathematical problems, of proving whether this property of your program holds or doesn't hold, or proving whether your mathematical proof is right or it's not right, can broadly lie somewhere on the spectrum with two ends. At one end of the spectrum, you have problems that can be solved algorithmically, but are very difficult for humans to do or humans to confirm because of their size. So for instance, in maths, you might have this expansion. Okay, you can work through most people who haven't done it for a while and are doing it every day would probably make a mistake. If this had, thousands of brackets, then there's no way that a human's going to be able to go through and check it. But an algorithm can go through and check and prove that the two sides are equivalent. So in software, you might want to check that every single execution path through your program has a test case. So coverage checking. And this is an example of something that is, you can do algorithmically, but a human would never want to do themselves. On the other hand, of the other end of the spectrum, you have the problems that are super difficult to solve algorithmically because they require some nebulous concept called insight. They require taking, results from lots of different areas or, reasoning about global properties of a system that, you can't capture algorithmically. So in maths, you might, for example, if you're trying to prove that, Euler's identity, e to the I pi equals 1, it's difficult to imagine that an algorithm that would come up with that based on the simple rules of arithmetic and complex numbers. Maybe you could, but it's not clear how to do that easily. In software, you might want to prove that an OS scheduling algorithm is fair, in inverted commas. So, that every program gets no more than twice the amount of time on the CPU than any other program, for instance, over a long period of time. And proving these properties require insight. That it's very difficult to come up with algorithms that can do these automatically. So we are going to look, to start with, we're going to look at the first class of problems. So those problems that can be solved algorithmically. And these are tackled by a class of theorem provers called automatic theorem provers. And it sounds terribly clever, but, and some of the algorithms that they use are terribly clever, but they're very simple at when you get down to it, is automatic theorem provers. Each one specialized at solving a particular mathematical problem. They have an algorithm that does it, and they spit out, yes, the algorithm says yes, or the algorithm says no. The classic example of these is a SAT solver, which is satisfiability solver. And this problem actually lies, many problems in software can actually be reduced to SAT problems. And this says that if you take the SAT problem is you have a list of Boolean variables, x1, x2 to xn. It can either be true or false. And you're trying to decide whether there exists an assignment to the variables that satisfies a given formula. So whether you can say x1 equals true, x2 equals false, etc., and then the resulting end of the formula is true. And there's lots and lots of SAT solvers that do this, and you put in the formula and it either spits out, yes, it's satisfiable and gives you an example assignment, or it says, no, it's unsatisfiable. Another example of an automatic theorem provers are SMT solvers. And SMT solvers are an extension of SAT solvers where the Boolean variables are instead replaced with Boolean valued expressions and the variables can now belong to different sets. So for instance, the variables might be over the integers or the reals or some other set that you're interested in. And SMT solvers can solve expressions, that involve inequalities or equalities, as well as logic things. And again, you feed in the expression and it says yes or no.
So
satisfiable, unsatisfiable.
Could you give me an example when you apply this to software testing, right? So I guess that's the main application area. What sort of software problems can you solve with SAT solvers, and what sort of problems can you solve with SMT solvers?
So you can solve, well, there's a difference between, so the case of using SAT and SMT solvers for formal verification, there's various examples. You can also use SAT and SMT solvers to solve particular, as algorithms to solve particular problems as well. An example of where you might use it for formal verification is in software is actually the coverage checking one. You can reduce it to, you can reduce your code and say you can assign each path through the code as a variable, and you can assign, you can assign each path through the code as a variable, whether or not it's visited as a variable, and you can formulate the transitions as, as a implications, and you can throw it all into the SMT solver and you can get it out.
Okay, thank you. Just helps me understand the problem a bit better. Okay.
The issue with automatic theorem provers is that obviously not all mathematical problems have algorithms to solve them. Both SAT and SMT solvers are guaranteed to give you the right answer. So if you give it a problem that is satisfiable, it's guaranteed to return satisfiable. And if you give it a problem that's unsatisfiable, it's guaranteed to return unsatisfiable. However, many interesting classes of problems are undecidable. And what this means formally is that it is a mathematical impossibility for an algorithm to exist that solves all instances of the problem. So it's not just that we're not clever enough to come up with an algorithm, it's that such an algorithm cannot exist. And it's actually really easy to get into undecidable territory. So for instance, if you take your SMT example and then you add transcendental functions, so like sine, cosine, ln, exponentials, and you're now trying to solve saying whether these expressions are satisfiable, this is now undecidable. There's no algorithm that can give you the correct answer 100% of the time. So when you hit undecidability, what you have to do is you have to compromise, and you have to say, okay, we're going to have an incomplete solver. So you don't want to sacrifice the soundness, which says that you don't want to, if it returns that it is satisfiable, or if a property is true, you always want it to be true, right? But you instead, what you do is, if it says that the property is false, well, then it might be true or it might be false. You don't know. Okay. The algorithm is unsure. So you can trust the true answers, but you can't trust the false answers. And this sometimes gets us quite a long way into terms of, you can solve quite a lot of the subclasses of problems, but you're never guaranteed to be able to solve all of them.
Okay, so false could be false negative or false positive in this case. Okay.
Yes, so it's false. Yeah, it's so they accept false negatives rather than false positives, usually.
Okay, but true is never are false positives, they're always true. Okay, cool.
However, even if you restrict yourself to the set of decidable problems, most of these problems, the algorithms for solving them are NP complete, or actually even harder. And therefore, they tend to be, in the worst case, horrifically expensive. So that, the behavior is exponential in the length of the, so if you exponential in the length of the formula that you're trying to satisfy, for instance. So you add one extra variable and suddenly it blows up. Interestingly, in many practical applications, the worst case doesn't occur, or you can use clever heuristics for deciding how to solve these problems that, most cases avoids the worst case, this exponential blow up in performance. And what this means is that actually, for examples that occur in real world, they can actually handle remarkably big ones. So, 10,000 variables, expressions, millions of lines long for SAT solvers.
Do people do things like then, trying to simplify the problem using heuristics, try to map it to a solvable problem, sort of, make simplifying assumptions, but then, the trade-off is then to show that the simple model sort of substitutes, or these heuristics sort of hold for the more complicated model.
Yeah, that's definitely one approach. In another approach is just to go to an incomplete solver and get performance, sacrifice, say you're sometimes going to get false negatives, but that allows you to make assumptions that would allow you to drastically simplify the problem. Okay. Regardless, if you make your problem too big, even modern automated theorem provers would choke. Like, you can't postpone the exponential behavior forever. It's going to bite you at some point. Finally, the kind of another drawback of automatic theorem provers is that the output of the theorem prover may not actually improve our understanding on any level. If it returns unsatisfiable, there are no assignment of variables. Often these some theorem provers do try and return information, but many theorem provers will just say no, and it doesn't actually give you any idea of why it wasn't satisfiable or why the property didn't hold it. It just gives you a yes/no answer. So what if we're trying to solve problems that require insight? What if we're on the other end of this spectrum? Well, in this case, what we usually do is we resort to interactive theorem provers. And the core concept of an interactive theorem prover is that you, the user, provide the proof and the computer checks it. So the computer is not responsible for proving property, you're responsible for proving it, and the computer will check that each of your steps are valid and you haven't made any mistakes. And the advantage of this is that you have a much wider range of proofs, and that you do actually get informative, the proofs that you get, because they've been written by a human, they're usually human readable, so you can get insight. You can look at the proof and you can get insight into why the thing is true. Depends on the theorem proving, on the language or on the theorem prover. Sometimes the syntax is more readable, sometimes it's less readable. The disadvantages are that a basic interactive theorem prover is not automatic. In practice, most interactive theorem provers incorporate automatic theorem provers inside of them, so that you can say, okay, this is the proof for the difficult steps, 1, 2, 3. The step from 3 to 4 is, one of the examples of, is an example of a problem that an automatic theorem prover can solve. So apply the automatic theorem prover, and therefore we have a proof of the entire property. So yeah, interactive theorem provers are user guided rather than automatic.
And you need special languages for them. That's that Isabelle and Agda.
Yeah, and Coq and Hole and Agda and Lean, and they're all, each of them come with their own special language. Okay. Some of them incorporate existing programming languages into them. So for instance, that you can write ML or and then reason about your program written in ML if the theorem prover is integrated with the language. And then on the other hand, some of them have languages which you can write both programs and proofs. So you write your program in the same language as you write your proof, which is examples like Agda. Out of interest, just a shout out to Wen, who Wen's recent work has just been to incorporate automatic theorem provers into Agda for the first time.